Good morning. Here we are at the physics video lecture. Physics 105A video lecture 4. So let's begin. We're talking about coordinate systems and kinematics. So let me go ahead and start with what we're always working on. Newton's law. I just introduced those two dots for the second time derivative last time. So we have Newton's law, and it is going to involve forces that we already talked about, vector nature of forces, there's inertia, and the second derivative position. We're talking about kinematics, and we're doing a study of kinematics in plane polar coordinates, and we're going to move on from those. But first, let's wrap up the plane polar coordinates. So, plane polar coordinates we'll have our picture here once and for all. There's our x and y Cartesian axes, and we have a vector. There's an angle phi. There's the magnitude of the vector r. And therefore, just out of geometry, we have x is r cos phi, y equals r sine of phi. And what we found is we could write the vector r is equal to its magnitude times the unit vector. And the unit vector r hat is just cosine of phi, sine of phi. Okay. But now r and phi are functions of time. So then we went ahead and found the velocity. So next, we said the velocity, which was r dot, turned into r dot r hat plus r phi dot phi hat. And this unit vector phi hat was equal to minus sine of phi and cosine of phi. Minus sine of phi, cosine of phi. And so if I attach these two vectors here, say with red, if I attach them to this point, there's my r hat, and there's my phi hat, and they are constructed to be orthogonal to each other. So r hat and phi hat are orthogonal unit vectors. So what we still had left to do was to find the acceleration. Good? So I'll write finally acceleration. And we're just going to differentiate this expression. So acceleration is equal to time derivative of v. So we're just doing chain rules, product rules. So we have r second derivative r hat plus r dot r hat dot, and then here we have r dot phi hat plus r phi double dot phi hat plus r phi dot phi hat dot. So I've just done the product rule for this whole thing. And now we have one unknown quantity here. We have phi hat dot. So we have to take its derivative. So since we have phi hat right here, its time derivative is just going to be minus cos phi dot, minus cos phi dot, and here it's going to be minus sine phi dot. And we see something interesting. we can pull out a minus phi dot common to this, and then we're left with minus cos, or cos phi sine phi, which was r hat. Okay, so for that reason, I'll skip that step. I mentioned it, minus phi dot r hat. So now we can put everything together. Because r hat dot, which was in here, note r hat dot was equal to minus sine phi dot. So that was phi dot phi hat. So now we can put it all together. Good. So this gives us, this leads to our acceleration being, we have our second derivative. Here we're gonna, here, once more. We're just gonna find the coordinates in terms of r hat plus phi hat. Okay, so we should be able to pull this off now. We have our second derivative for the r hat, and then we have r phi dot phi hat dot, so it's going to be r phi dot another phi dot r hat. So we end up with r double dot plus minus, remember we got that minus sign in there, minus r phi dot squared, so r hat, and then for the phi hat, we have, we're going to have this one here, phi dot phi hat, so r dot phi dot phi hat, but we're going to have a second one, r dot phi dot phi hat. So there's going to be two of these, and then the other one, r phi double dot phi hat. So there's our acceleration. Put it all together, and you can see the acceleration has a component in the r hat direction and in the phi hat direction, just like the position and velocity have components in the r hat and phi hat. Now you might think that we're going to have to chase these things around and it's going to make life complicated, but that's in fact not the case. Okay. When it comes time to use these coordinates in a concrete case, we always choose them because they make life easier. So let's go ahead and put all three of these together on top of each other now that we've obtained our result. And so finally what we have, so plane polar coordinates, we can put them all in one corner here and work with them. So in fact I'll reproduce everything we've got here just in small. Right. X, Y, phi, r, and r hat, phi hat. And so what did we have? We had r is equal to r hat, v is equal to r dot r hat plus r phi dot phi hat. Now v squared we did last time. That's actually an interesting one. Of course, it's the square of a vector, which is a scalar, dot product with itself, and that was r dot squared plus r squared phi dot squared. We'll use that a lot during the semester. And now we have the acceleration, which has these two components, r hat, phi hat, so r double dot minus r phi dot squared, r hat plus 2r dot phi dot r phi double dot. We'll just do a little practice with both of these, with all of these expressions to make sure they make sense. And I'll even put in the r hat is equal to cos phi sine phi, phi hat is equal to minus sine phi cos phi. Good, so there's a complete set. Consult, make sure I got it all right there. Yes. Good. So now we'll do some examples. Because what you're going to see is we actually run into familiar material very quickly here. Okay. So the example that we'll start with is just uniform circular motion. So uniform circular motion is something we've all studied, and this formalism is just made for it. Okay. So when we have uniform circular motion, since we are on a circle here, I could say of radius capital R, just to be concrete, then right, the radius vector, of course, is just going to be capital R times R hat, and what we'll have is phi of t being what changes, right? So here, actually for completeness, let me go ahead and put here R is equal to R of t, V is equal to V of t. Okay. Yeah. Good. So let's go ahead and talk about uniform circular motion. Here, R is equal to capital R is constant, and phi, since this is uniform, is just going to be equal to omega t. Okay. Where omega is equal to 2 pi over capital T, where t is the period, time period of one, go around the circle. So let's see what we have here. R, the vector now, is equal to R cos omega t, R sine omega t. If you were to go back to Cartesians, let's look at the velocity. R dot R hat. So R dot is going to be 0. So the velocity is going to be R, but what's phi dot? Phi dot is just omega. Okay, derivative of d phi dt is just going to be omega, so it's R omega phi hat. Okay, so let's use this vector again. So at some point here, our velocity is, of course, always tangent to the circle. Phi hat is tangent to the circle and is a unit vector. So the velocity is R omega phi hat. Its magnitude is just R omega. Or, yeah, we'll just write R omega. We'll just keep omega being constant, positive. Okay. It's just R omega. So that's the velocity. And we would also have that right at the velocity squared. It's square root R squared omega squared. Okay. What about the acceleration? For the acceleration, going around in that circle there, we go ahead and study this, and we realize that, we'll look at this part here first. R dot is 0. Okay? Phi double dot, second time derivative of phi is 0 because the first time derivative is omega, it's a constant, second is 0. So we have no phi hat component for the acceleration. Our second derivative is 0 as well, so we end up with minus R phi dot squared. So in this case, we end up with minus R, and remember phi dot was omega, so R omega squared. And what about the direction? R hat. So this is your centripetal acceleration that you guys learned about in the past. R hat points out, minus R hat points in towards the center, and this minus R omega squared is the acceleration. So let's take that one step further. We have minus, now we've got the R, but the omega can be expressed as V divided by R. I'll go ahead and put that here as well. V divided by R. So when we square it, we have V squared over R squared times R. This is the minus V squared over R hat. So the minus sign gives the direction towards the center, and this V squared over R is familiar to you guys as the expression for the centripetal acceleration. Okay. So you see everything just falls into your lap here when you carefully plug in these particular definitions here. So I'll put that as a note. This is the familiar V squared over R expression. Okay. And in fact, this V equals R omega may be familiar to you guys as well. Good, so that is how we work with plane polar coordinates. And we'll do these towards the end of the semester pretty thoroughly again when we talk about the central force problem, the Kepler problem, kind of the high point of our first semester career here. And we'll have a little use of them in the meantime as well. Okay. We can talk about pendula, physical pendula, and the simple pendulum using these coordinates just as well. Okay. So they're very useful. And there you have it. Okay, now we're going to extend these ideas to cylindrical coordinates and to spherical polar coordinates. The cylindrical coordinates, we can actually just we can define and write them down and basically inherit all of these results. The spherical polar ones will cause us a little more work. There's a little more to do. But we'll do the cylindrical coordinates first, as it makes a good point. So cylindrical coordinates. Yeah, so just as these plane polar coordinates, anytime you're working with something that moves on a circular arc, these are candidates to make life actually easier. And cylindrical coordinates if you're working on a cylindrical surface for one reason or the other. And if you have axial symmetry. Now, let's go ahead and define them. So this time, we're going to have our three dimensions like this, x coming out of the board. And we'll take a vector to say, here, there's an R, but we have to define its projection into the plane here. And it'll have a z component. So I'll define an angle phi with respect to the positive x-axis, which is just what we had before, but I'm going to designate this projection vector as rho, the length of that thing, and now you can see that we're going to have, go ahead and write it this way, R is equal to rho cos phi, rho sine phi. See, I've just chosen a new letter. This would be generally our plane polar coordinates. But then in the third dimension, we just have z, a third Cartesian coordinate. And now this is going to be very easy. We're just going to inherit what we have up here. The velocity, which is our dot, we've already done all the work, really. It's going to be rho dot rho hat plus rho phi dot phi hat plus z dot. And I can either say z hat or k hat. One's as good as the other. I'll go ahead and write z hat for the unit vector in z direction. So let's go ahead and define these things. We've got rho hat is equal to cos phi sine phi. Phi hat is equal to minus sine phi. Cos phi, just what we had before. And of course, z hat is, I see, 0, 0, 1. Okay, so here's what I forgot. We're in 3 dimensions, so 0, comma, 0. Okay, so yeah, that easy. And all 3 of these are unit vectors, and all 3 of them are orthogonal, and all 3 of them form a right-hand system. I'm going to make that a homework assignment in a moment. So I'll leave room for that there. And I'll continue this discussion up here. Namely, we still need the acceleration and the v squared. V squared is easy. So v squared, v dot v. See, because these 3 vectors are unit vectors and because they're all 3 mutually orthogonal, which is clear, okay, we already proved it for these 2. This one is definitely just out there, orthogonal to the other 2. Because of that, the square of this vector is just the individual components squared. So again, it's just the rho dot squared, rho squared, phi dot squared, plus z dot squared. And for the acceleration, we're going to have, same as before, so rho hat, phi hat, plus z second derivative, z hat. Yeah, so we'll have rho double dot minus rho phi dot squared, 2 rho dot phi dot plus rho phi double dot. Okay, so there's our acceleration again. Same as before with the addition of that perpendicular coordinate in the z direction. Okay, so as far as the homework goes, I just want you to show, first of all, and this is trivial, we've done it, but just for completeness. You know, when you do a problem like this, make sure you write it out thoroughly so everything to be defined and discussed is on your page. Show that rho hat, phi hat, z hat are orthogonal unit vectors. Okay, they're trivially unit vectors, and they're pretty much trivially orthogonal vectors. That means the dot product between any pair of these is equal to 0. Okay, that's what orthogonal means. So they're all mutually perpendicular. So yeah, you just knock that out. The next thing is that they form a right-hand system. Show that rho hat, phi hat, z hat form a right-hand system. Now we talked about this. We talked about this with I hat, j hat, and k hat when we were doing Cartesian coordinates. Okay. So here we want rho hat, that is to say rho hat cross phi hat is equal to z hat and cyclic. So I'll just write recall for I hat, j hat, and k hat. I'll just do the little picture here. I, j, k. For these we saw that I hat cross j hat equals k hat. So we had I hat cross j hat equals k hat and cyclic. So, and then you go through j hat cross k hat equals I hat and k hat cross I hat equals j hat. So this is something we had in Cartesian coordinates. And if you hadn't seen that, you may want to actually just do it, because you know these are easily defined. But the same thing should be true for this combination. Okay. So looking at this picture, rho hat cross phi hat is the one that's coming out of the board, right? So rho hat cross phi hat should be equal to z hat and cyclic. So they form a right-hand system, you do them cyclically. Okay. So yeah, when you have unit vectors, orthogonal, right-hand system, then everything just works automatically in terms of the vector properties. Good, so that's a homework. I'm going to consult the clock. And we're going to move from the cylindrical, you know, we've got the plane polar, got them all up on the board here. Matter of fact, plane polar, cylindrical, move on to the spherical polar coordinates, which is where it gets even more interesting. Okay, so cylindrical, spherical polar coordinates. And again, we have to find the kinematic quantities for position, velocity. Turns out on this one we don't need the acceleration, but get ahead of myself. So spherical polar coordinates, first of all, we have to draw, same thing we had here for the cylindricals. We've got our x, y, and z axes, and we take a vector, r, that's the point that it's pointing at, and again we project it down onto the xy plane. And again we measure this angle phi with respect to the positive x-axis, but we're also going to measure this position z in terms of this polar angle theta. So now we have to write out what we have here. We have r vector equals, I'll start out as an ordered triple. So we have r cos, no, not r cos, we have r sine of theta to give us the length of this projection down here. So r sine theta cos phi for the x component, r sine theta sine phi for the y component, that projection down there, and then r cos theta for the z component of the projection. Good, and we want to take derivatives of this, but now, you know, we have r function of time phi is a function of time, and theta is a function of time, because that's where we're headed with this. So the first thing we do is write r is equal to r hat again, and our unit vector r hat is everything where we've pulled out the magnitude. So just by construction, it has to be a unit vector, but of course we're going to want to show that anyway. So we have sine theta cos phi, sine theta sine phi cos theta. We want to show that that's a unit vector. But now we need the velocity and the acceleration, except there are reasons that we don't need the acceleration, and we'll actually learn those next semester. So for this system, it's going to suffice to just take it to the velocity. Acceleration you can look up or figure out on your own, but strictly speaking, the way we're doing mechanics, we won't need the acceleration in these coordinates. Good. What about the velocity? V is equal to r dot r hat plus r hat dot, and we can see that the time derivative of this thing is going to cost us a little bit more work. R hat dot is equal to, we do each slot here separately. So we have cos theta dot cos phi plus sine theta negative sine phi dot. That's the first one. Then we have cos theta cos phi. I'm sorry. Okay, cos theta sine phi. And actually, I should pull that theta dot out under. So I'm differentiating here. So sine theta is cos theta dot sine phi plus sine theta cos phi dot. And the third one here, I have minus sine theta dot. Okay. That looks like kind of a mess. What we're going to do is pull out the component of this vector that is proportional to theta dot and the one that's proportional to phi dot. Okay. So there's phi dot here and theta dot. So let's see how that works. So the one that has a theta dot would be cos theta cos phi comma, and then cos theta sine phi comma, so theta dot there, and then minus sine theta. And then this next one, we'll pull out phi dot, and let's see what we have here. Phi dot will have minus sine theta sine phi, sine theta sine phi. We'll have sine theta cos phi, and we'll have 0. Okay, so let's send this up and keep working. Okay, now We also have sine theta common right here. So let's go ahead and work on the second one of these. So we actually could say we have sine theta phi dot times minus sine phi cos phi and 0. And over here, I don't think we can do that. Yeah, theta dot cos theta cos phi cos theta sine phi minus sine theta. Okay, so we're actually looking at our unit vectors now. Namely, we have r hat dot is equal to theta dot, and this is going to be theta hat plus sine theta phi dot, and this one here is going to be phi hat. In fact, you'll recognize this as our previous phi hat because it's minus sine phi cos phi. It's got the 0 there. Okay. This theta hat's a little bit different right there, but this should suffice for us to write down what v is. Okay, all this work was just to get r hat dot, and now we want to get v. Okay, I'm going to consult here briefly. Yeah, that should do the trick. Fantastic. Good. Those are them. So let's go ahead and put this together now, and then we'll put them all on the left side of the board there. So now we have v r dot r hat plus r hat dot. So we have v equals r dot. It's going to be r hat, and then we're going to have r hat dot, so it's going to involve these two as well. So r dot r hat plus r hat dot, so it's going to be r theta dot theta hat plus r sine theta phi dot phi hat. So there's our first derivative. Now, if you want, you can pursue this to get the acceleration. We already know what r hat dot's going to be, but then you're going to have to get theta hat dot and phi hat dot. We're not going to go there because for mechanics, the way we're going to do it next semester, everything that we need will be derivable from the velocity and the velocity squared. But what we do need is the velocity squared, and also we have to look at these and make sure we understand what they mean. So first of all, put the velocity squared here. So v squared, the dot product with itself, under the assumption that these are mutually orthogonal unit vectors, and they are. I'm going to have you guys prove that. Under that assumption, we just square these coefficients. So we get r dot squared plus r squared theta dot squared plus r squared sine squared theta phi dot squared. So I think we have a sufficiently complete presentation here, and I'll add another homework problem to the mix. Homework. Actually, before we do that, let's draw a little picture and discuss this briefly. Yeah, I'm just going to duplicate that picture up there down here with slightly different designations. Good. So here we have our x, y, z. Here we have that vector r. There's our theta. Projected down to here. There's our phi. Yeah, so the question is, where are these unit vectors? What do they look like? Now the r hat is clearly pointing out that way. The theta hat, you can imagine getting that because it's, where's the theta hat? The effect of it, by the way, because of the effect of it right here, r theta dot, you can see that the theta hat is sweeping out. It's, imagine if you were to sweep out increasing theta. So your theta hat is in this direction. Oops, that's theta hat. And the phi hat is sort of if you were going in a circle this way. Good luck. Okay, you guys do a better picture. That is not quite doing it. Yeah. So the phi hat is actually into the board. Phi hat would be into the board somehow, and I'm having trouble with the perspective on that one. Nonetheless, what I want you guys to prove is that these three vectors, this is our theta hat, this is our phi hat, and the r hat is right up there. You want to show that they're all three of them unit vectors. This one is trivially a unit vector. And you want to show that they form a right-hand system, orthogonal right-hand system. So we'll write this out and then I'll get us started. In fact, I'm going to consult the clock first here. Yeah, running right up against it. Okay. So homework. Show that r hat, theta hat, phi hat form a right-hand orthonormal system. Orthonormal system, by which I mean coordinate system, right? Coordinate system. So what that means is we should have, first of all, normal means they're all three unit vectors. So that means r hat, theta hat, phi hat are unit vectors. First of all, and this orthonormal system means that these cross products are always going to work out. So we should have r hat cross theta hat equals phi hat and cycling. You just cycle through them. You always take this one, bring it to the front, cycle through them. Just like I hat, j hat, and k hat were an orthonormal system. And to do that, you just use your determinant rule for 3x3 matrices and cross products and stuff like that. So it shouldn't be bad. What you'll see is, say you want to show that theta hat's a unit vector. Okay, you got cosine squared theta, cosine squared phi, plus cosine squared theta, sine squared phi. So you got your cosine squared these two, cosine squared and sine squared, add up to 1, and then you've got cosine squared plus sine squared adds up to 1 as well. Okay, so the unit vector nature of these is not difficult to get. And then the cross products you just have to do and make sure you always get that next vector. The cross product of one gives you the other one. Okay, that's enough for now. What we'll do next time is probably say a few more words about this and then move on into one-dimensional Newton's law problems. Okay, see you guys next time.